Hey, what's up? I want to look through these homework problems, but first I have to introduce you to a little friend of mine. Roll, roll, heuristics. Let's run. So here's Coco, the beautiful. Here, let me get a better view of him. There he is. It's a good-looking dog, isn't he? He's just chilling here. He likes to leave traces around the house that we've known he's been there. We prefer that he not do that. So you have any ideas other than beating him mercilessly, which we do, then those ideas would be very helpful. Ooh, let me get rid of this. Okay, let's go. I think we started with number 1. I have a bunch of windows open here. Hopefully I can manage this. So Bernoulli trials. Do these situations involve Bernoulli trials? Well, let's look at the definition of Bernoulli trials. This first one, we roll 50 dice to find the distribution of the number of the spots in the faces. Bernoulli trials have to be a success or a failure, and what is a success and what is a failure doesn't necessarily have to be a success and a failure. We're just looking for 2 different outcomes. Part A here has 6 different outcomes. No dice. But seriously, there's more than 2 possible outcomes, so no way. Sorry about that. Part B, so part A, because you have more than 1 possible outcome. Or more than 2 possible outcomes, sorry. It can just be success and failure. It's more than that, no way. How likely is it that a group of 120 in a majority have type A blood, given that type A blood is found in 43% of the population? So this will be okay. You have a success and a failure. Even though you have many different types of blood, you could say type A is a success and not type A is a failure. So you could model it that way. That's fine. Let's see here. They have we're assuming independence with 43% of the population. They give you the percentage as well, or the percent chance. So that's fine for B. It's good. Very, very good. So long as the 120 again is less than 10% of the population, then in a group of yeah. It just says the population. It doesn't say in particular what it is. So we'll assume the world population, which is about billions and billions of people, and 120 is certainly nowhere near 10% of that. So just want to reread that real quick to make sure. We deal 7 cards from a deck and get all hearts. Sorry, I get a very earnest Coco here. How likely is that? For C, I think this violates the 10%. On a card, you have 52 cards, so 10% is 5.2, so 7 is too much. You cannot assume independence, and because 7 is more than 10%, we're not even going to say that we're going to, let that little bit slide. It just goes too far. Okay, maybe Coco will leave me alone. Oh, sorry. No, I don't think he will. Oh well. You'll just have to continue to hear small feet wrestle around while we do this video. We wish to predict the outcome of a vote on the school budget, and a pool of 500 or 3,000 voters likely favor the budget. Let me see here again. Are we violating that 10%? Yeah, 10% is 300, and this is 500, so it's too big of a sample for us to assume they're independent even when they're not. Remember, we can, even when things aren't independent, we can assume they are as long as we don't go beyond 10% of the population. So no way with that one. Part E. A company realizes that about 10% of its packages are not being sealed properly. In the case of 24, is it likely that more than 3 are unsealed? So we have success and failure. I guess we'd call sealed a success and unsealed a failure, but we could call it the other way. We just need 2 different sides of some coin, however we want to call it. So what we define as success and failure doesn't have to be success and failure in some context. It can be, whatever. So let's see here. In a case of 24, is it likely that more than 3 are unsealed? Yeah, the probability is 10%. You have 24 there, so this would be a binomial distribution because you have a set number. But I mean, you're assuming that there's lots of these cases coming out of the factory, as factories make lots of cases of things in general. So that's cool. I'm not worried about that. So 10% of its packages, you have your percent chance of failure or 90% chance of success, as we'll call it. You're given a number. Yeah, that's fine. So part E is fine for number 1. Okay, Bernoulli 2, these situations involve Bernoulli trials. So 2A, you're rolling 5 dice and need to get at least 2 6s to win the game. And this is cool. You have success and a failure. You have success as a 6 and a failure as not a 6. That's okay, and this is a pretty classic binomial distribution. Uh-oh, here he comes again. Oh well, he just likes to play a little bit, and he'll be satisfied for a minute or two, hopefully. So that's okay. The probability is constant. The trials are independent. They're dice. We always assume the dice are independent when we throw them. Dice cannot talk to each other unless wizards are involved. In that case, you have this lurking variable, aka a wizard, but we don't have any wizards here, so we're cool. Where was I? A is good. Bernoulli. B, we record the distribution of eye colors found in a group of 500 people. There is no success and failure here. So it's a number of different categories. I can't just put them in 2 different categories with a percentage, so no way. Part C, a manufacturer recalls a doll because about 3% have buttons that are not properly attached. Customers returned 37 of these dolls to a local toy store. Is the manufacturer likely to find any dangerous buttons? They could be properly or improperly attached. So that's okay. I'm going to assume 37 is less than the 10% threshold, so that's okay. Oh, a company recall. Okay, so a company recalls this word recall here slipped by me the first time I read it. Recalls mean that they said, hey, everyone bring your stuff back to the store right now or you're in trouble. Right now, bring them back. So the people who are returning them aren't necessarily returning them for any reason, but that the manufacturer said, hey, bring all of these back and bring them back now. Okay, so that's why they're bringing them back. So that there may be some connection between the dangerous buttons and people bringing them back, but the recall also indicates that they should just bring them back anyway. So that's okay. You have success and failure. I assume that we'll call success an undangerous button. Failure a dangerous button. But whatever, it doesn't really matter, right? You can switch the P and the Q. That's okay. So you have that percentage. 37 is less than 10%. You're good. Let me see. Again, D. Let me see. City Council picks a committee of 4 at random. So the 10%. It's you're selecting too much of your population. I was going to make some joke about success and failure, Republican, Democrat, making some connection there. But we don't even get to that. What a sad day. Oh, that makes me real rad. That makes him so sad. I don't know if you caught that dog speak there. But yeah, it doesn't matter. You're selecting 4 out of 8 and 11, 4 out of a total of 19, more than 10%. Doesn't apply to the 10% condition. Probabilities change too much. We could solve this problem in other ways. All right, I'm just saying that it is not a Bernoulli trial. That's what I'm saying. It's not that. We can still do that problem. That's okay. but it's not a Bernoulli trial. That's all I'm asking here. We're not solving any of these problems, all right? Okay, cool, good. I'm glad I got that conveyed to you in a good way. Oh, this dog is very impatient. Okay, a 2002, let's do part E. A 2002 Rutgers University study found that 74% of high school students have cheated on a test at least once. Ooh. Your local high school principal conducts a survey in homerooms and get response that admit to cheating from 322 of the 481 students. That's kind of terrible. I think so far as Bernoulli being satisfied here, I think that's fine. We're saying that 74%, that's the percentage that we're using. We're assuming that's true, which we often do. Even when we're trying to show that it's not true, we often start by assuming it's true. We'll get into that later with our null hypothesis. Let's see here. Let me see. So 481. I guess it really depends on the size of the school. At East Side, would that be less than 10% of the students? No, that wouldn't be. The book says it's okay, but they say, well, this is less than 10% of all students, the 481. This is so if your school has 4,800, let me see, times 10 would be 4,810. So if your school has 4,811 students, that's okay. If it has less, like our school does, then it's not okay. So I guess this one just depends on the size of your school. So the book says it's okay. At East Side, we would say this is not okay. This is not big enough. Or I'm sorry, it's too big. The school isn't big enough for this scenario, for that 481. So a little bit of a discrepancy there. So there was 1 and 2. Let's jump to number 9, and I hope you're enjoying the PDFs in the book folders. They're there for you to use and abuse. I'm not letting you download them. I don't have permission to do that. All these permissions things are fairly shady, and I'm just not allowed to. So sorry. Let me see. Number 9, hoops. A basketball player A basketball player has made 80% of his foul shots during the season, assuming the shots are independent, which they're not, but we assume. Find the probability that in tonight's game he misses for the first time on the 5th attempt. So that would be, this is geometric because you're going and you're assuming that one thing happens until something else happens. Fail, 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 succeed at some point. That's A and B. And the answers for C are weird, but we'll go over that in a second. So A, he misses for the first time on his 5th attempt. So it will be make. It will be 4 times he makes it, and then he misses it. Okay? So that would be 0.8 to the 4th power, and then times 0.2. It will be, and you have to realize here, they're kind of between A and B, and C, they're changing what, the success and the failure are, because the geometric model says fail, 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 succeed. But what a failure and success is not always what we call failure and success in the context of the problem. So missing for the first time on his 5th attempt, this would be a geometric model with a probability of 0.2 because it's the 5th attempt he's going to miss, and that's the probability we're concerned with. So it would be 0.8 times 0.8 times 0.8 to the 4th power, failure to the 4th power, times 0.2. And that gives us, I'll drag this up here until we can see it. There we go. I'm not going to show you the rest just yet. So it is 0.8 to the 4th power, then times 0.2. The probability of a failure, even though that's making it, to the 4th power times 0.2. Okay. Makes his first basket on his 4th shot. So failure, 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 makes it. Now our probability is 0.8 because the success at the end is that he makes it this time, not that he misses. So it would be 0.2 to the third power, failure to the third, the fourth minus 1, failure to the 4 minus, so failure to the third power, 0.2 to the third power, times 0.8. And let me bring that up as well. Coco! Sorry. So let's see here. Good. 0.2 to the third power times 0.8, 0.0064 is what it comes out to in the end. Okay? He makes his first basket on one of his first 3 shots. The book has a way to do this. I think it's kind of silly. It's a lot easier just to find the complement. So if he makes his first basket on one of his first 3 shots, that is the opposite of missing his first 3 shots. So 1 minus 0.2 to the third power gives you the same answer the book has. The book said, well, let's say the probability that his first shot is on the first basket, his first shot is on the second, his first shot is on the third, and then all those up, and that's silly. I can mentally tell you 0.2 to the third power is 0.008. Subtract that from 1. That will give you that same answer. So 0.9, no kudos to the book on that one, or maybe they just wanted you to use this model here, but I just can't do it. It's inappropriate here. It's a lot easier to think of it as the complement of another event, which is much easier to solve. So the opposite. Whoops. Oh my goodness, did I search something in Google? I don't know. It's crazy, these Macs, huh? Woo! That makes his first basket on one of the first 3 shots. The opposite of that is that he misses the first 3. 1 minus that, bada bing, bada boom, go. A lot easier. Next, let's look at number 10. Ooh, 17 minutes. We're pushing time here. Let's see. See if we can get this done. Number 10. Good, yes. So, suppose a computer chip manufacturer rejects 2% of the chips produced because they fail pre-sale testing. So what's the probability that the 5th chip in the test is the first bad one you'll find? So success here is finding a bad chip. Okay, so my probability is 0.02. So 0.98 to the 4th times 0.02 will give me that. Let me, here we go. Dun, dun, dun. And that gives you it. So X, let me see, failure, aka finding a good one, is 0.98 to the 4th power for the first 4, and then 0.02 for that last one. Okay, what's the probability you find a bad one within the first 10 you examine? And the book's answer is really super wonky here, and they say use a model on a calculator or a computer. We don't need a stupid model on a calculator or a computer. Hello? Let's just find the complement of this event. So you have, what's the probability you'll find a bad one within the first 10? The opposite of that is that you get 10 good ones. 0.98 to the 10th power, subtract it from 1, bada bing, bada boom, easy money, cha-ching. All right, I don't know why they did that, but super lame. 11 and 12, they say find the expected value for those. And let's just throw them up here, right? It is just 1 over the probability. So what's the expected number of shots until he misses? The probability of that is 0.2. So 1 over 0.2 gives you 5. So again, we're defining success in a funny way. Okay, we're defining success in a funny way. So how many do you expect to test before finding a bad one? The probability of the bad one was 2%. So 1 over that probability, 50 chips. The first bad chip should be the 50th. Okay, 11 to 12 made much better time. Let's go down to number 23. 24, 23. I'll tell you what, on these Macs, I love the two-finger move. It's great. When I'm on a PC, I miss it. I wish I had it. Awesome. Number 23 is using our definitions of, sorry, I'm scrolling here, using our definitions of mean and standard deviation. So let's see. Generally believe that nearsightedness affects 12% of all children. A school district tests the vision of 169 incoming kindergarten children. How many would you expect to be nearsighted with what standard deviation? So nearsightedness, 12%. We have our Bernoulli trial, and it's defined at 169 children. So this is a binomial distribution. When the number is defined initially, they might give you a number later in the geometric, but when the number is defined initially, it said, look, we are testing 169 children, then it's binomial. And we're going to have a certain number of hits and misses spread throughout there. So to do this, we have a couple of formulas. There's the mean is NP, the number 169 times the probability of 0.12. And the standard deviation is the square root of NPQ, the square root of the number times success times failure. Gave us 4.22. So that was 23. You need to recognize that it is a binomial because there is a set number of children, and right from the start, this has to be this many kids, and then go from there. 24, 24, let me look at... Okay, here we go. At a certain college, 6% of all students who live in a... Awesome. So we have this. This is our friend right here. I don't see the circles when I'm recording, but I see them later when I view them, and the circles are awesome. Awesome. So, 40 freshmen. This is binomial. 40 freshmen, the number is given, binomial, binomial, binomial. Okay? So, we're going to use those same formulas we used a minute ago. I know, super boring to use just the same formulas, but you should expect that by now because these paired problems are done in a similar fashion. All right, so NP, 2.4, square root NPQ, 40, good. Q found by subtracting 1 from the probability. Bam. 25 and 26. Let me see. Ooh. 25, 6 serves. These are both binomial as well. And they don't get into that normal model junk because the numbers don't get too big. We don't have 10 successes and failures, so yeah, neither of these, that's fine. And we'll do a little bit of that in a minute or two. Okay, so the probability that all 6 serves are in, we really could have said this before. If you have a successful serve 70% of the time, you get 6 in. It's just that. Order doesn't matter. They're all just perfect serves. So 0.7 times 0.7 times 0.7 times 0.7 for all the 6 of those. But to write it in terms of this still works. So let me just show you that, right? So you have 6 choose 6, because all 6 are in. And then 0.7 to the 6th, 0.3 to the 6 minus 6. 6 minus 6 is 0. So we could have done that before, but it still fits with our new friends here. It still works. It still works. It's very exciting. Okay, so exactly 4 serves in. So you have 4 in, and because it's exactly 4 in and 2 out. And then to compensate for the fact that you could get those 4 in and 2 out multiple different ways, we use this combination speak here. And so let me, so exactly 4, and I don't really have a good way to write here. That's why I keep just using my answer key. And it's easier, quite frankly. The answers are right there, you know. I mean, I'm not trying to cop out anyway. So here we go. 6 choose 4. And so that will account for the different ways in which those 4 serves can happen between the 6. 0.7 to the 4th for the set for the make, and 0.3 the failures to the 2nd power for the 2 that you didn't make. And that gave us 0.324. Cool. Yep. You could do that by hand, or you have your calculator function out to do that. Either one's fine. Again, I don't really have a good way to put that up here right now, so we could clear those issues up soon. Probability of at least 4 serves in, so it can be 4, 5, 6, or 4, 5, or 6. Those 3 different possibilities. Looking back here at the 4, here we go. Here is 4. We're seeing something extra there. Okay, exactly 4 in, so I need to do this for 4, 5, and 6, and then because they're disjoint, you can't get exactly both 4 and 5 at the same time. Then we can add them up. So we'll do this for 4, for 5, and for 6, and then add those up. Yes, so this will change. This 4 down here will change to 5 and 6. This 4 will change to 5 and 6. This 2 will change to 1 and 0. And we're going to add those up, and they have it all written out here. There we go. Okay, probably at least 4. There you go. And you have easier ways to do this in your calculator. I'm going to show you a little GeoGebra thing right now that will do it. But basically, you need to add those 3 things up somehow. You can do the combination functions in your calculator and just work it from there. Whatever you feel comfortable with. I think the book presents a variety of ways. So let me see. Let's bust out GeoGebra. Or like GeoGebra, yo. So let me see. This is actually for a future problem. N is 6. Probability is 0.7. And here is our distribution. So 4, 5, or 6. There we go. So 4 is between 5 and 6, 0.7443, which agrees with what the book says. Also for 4, it's 0.324, which is also what the book says. So looking over this distribution, everything, well, certainly looking down here at 0, 0 probably isn't going to happen. So if you're serving 6 times, getting absolutely none of them to come in if you have 70% of the time is very, very low. Let me see, 7/100th of a hundredth of a percent. Very, very, wait, no, 7/100th of a percent, sorry. Very, 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 very low. I read that wrong. 1% of the time, you'll get 1, 2, 5, 6% of the time, and this 4, 5, 6 scenario will probably happen. More than half, 74% of the time. I just like doing that. Sorry. Anywho, so that was was that it? Oh, no more than 4 serves in. So that would be no more than 4 would be 0, 1, 2, 3, and 4. So again, I guess I could just use my friend over here, right? 0, 1, 2, 3, and 4. What's this? Oh my goodness, didn't want to do that. Okay. 0, 1, 2, 3, and 4. And there we go. That's 0.5. Great. That agrees with the book. 0.5798. The book has 0.580 rounded off another decimal place. That's fine. So that is that is that one. And the way they wrote it out here, I probably wouldn't prefer this. I'd probably just take there's if you serve 6 times, you're either going to get 0, 1, 2, 3, 4, 5, or 6. And this is 0, 1, 2, 3, and 4. I would say just do 5 and 6 and subtract it from 1. I would find the complement, make that a little bit easier. Almost there. I know we're pushing a half hour, but hang in there with me. We just have one more. Ooh, a wildlife biologist. Now this sounds exciting. Okay, so examines frogs for a genetic trait. Ooh, scary. It's found in 1 of every 8 frogs. He collects and examines a dozen frogs. So it's telling you a dozen. You know n, you know the number, so it's not geometric. Because geometric, you go until something funky happens, or until your success happens. I guess that's not funky. So this is again going to be a binomial distribution. So let's see, none of the 12 frogs, at least 2, 3, or 4, no more than 4. Okay, so this is another binomial because it has a set number for n. Okay, none of the 12 frogs, well, that's the failure number. So 1 out of every 8 is success. 7 out of 8 is failure. So 7 out of 8 times 7 out of 8 times 7 out of 8 times 7 out of 8, 12 times. Because there's no variability in how they could occur. The book uses the formula, which is appropriate for binomials, and I get it, but 12, choose 0. If you have 12 things and you pick 0 of them, there's one way to do it, so that's 1. 0.125 to the 0 power, that's also 1. So you just have 0.875 to the 12th power. That's it. That's all you have. The rest of it goes away. Gone. Poof. Gone. Outie. Okay, so I don't have to worry about that. At least 2 frogs. Well, it could be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Forget that. Let's find us a complement. Let's find a complement. Ooh, let me look into the camera. Sorry. I look at myself instead of the camera. Let's find the complement, and that'll make this a lot easier. The book does not find the complement. The book does this insane. Well, I guess they have the privilege of doing the infamous ... So it says, here we go. It says, you can see what it's varying. It's 2, 2, 12 minus 2. 3, 3, 12 minus 3. And then this nice little ... which helps a lot, the ... believe you not. Okay, so what we need to do here is think about this a little bit, because I'm not doing this. This is crazy. Okay, a lot easier, find the complement. Okay, let's find 0 and 1, so we only have to do this twice instead of 10 times, or 11 times. Let's do 0 and 1, and then subtract it from 1. And I'm actually going to use a little computer help myself. Let me GeoGebra back out here. So we're still on part B. Let me see, we have 12. The probability of success is 0.125. Are we going with that? Was that what we defined as success? Okay. Oh. So between 2 and 12.45. Okay, this is correct. So you can see most of these trials added almost nothing, or to 4 decimal places, nothing to the total. So 8, 9, 10, 11, 12 are all really, 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 really small numbers. Just between the first 2, there's more. So what I would do is I would say find these first 2 numbers and get 0.5, 4, 6, 7 and be very happy about that. And then subtract that from 1 to get the book's answer of 0.453. That's my advice to you. I would find the complement of this event. Compliments are your friend. Okay, so the main thing here is at least 2 frogs. At least 2 frogs, there's too many ways. What's the opposite of at least 2 frogs? Less than 2 frogs. There's only 2 ways for that to happen. Okay, so 0 frogs or 1 frog. So that is much better. I like that a lot more. C, 3 or 4 frogs. I would just directly find 3 or 4 frogs. So 3, 3, and then 12 minus 3 is 9. 4, 4, 12 minus 4 is 8. Plug it in. Use your calculator or some other means. What do you think of that, Coco? Is that right? That's fantastic! Oh, good boy. Good boy. He really likes statistics a lot. I'm shocked. I'm shocked. No more than 4 frogs, so that would be 0, 1, 2, or 3. Is the complement easier? The complement would be 4, 5, 6, 7, 8, 9, 10, 11, 12. No, it's not easier, so I would just say 0, 1, 2, and 3 and add those friends up. So let's see what we got here. Oh, no more than 4. Sorry, 4 can be included as well, right? I'm sure you were screaming at me from the other end. Include 4, please! All right, I'll do it. So 0, 1, 2, 3, 4. Again, kind of a pain to type in, but manageable. Well, no, a bit of a pain in the butt. But you can do it. It's just a pain. Sorry. Let me get out my GeoGebra window again. Let's take a look at this. So 0, 1, 2, 3, 4, 90. A vast majority of the time, you're going to be between 0 and 4. Okay, most of the frogs are okay. Because, unless it's an endangered frog, then maybe we did take more than 10% of them, which would be super sad, but oh well. That is it for this video. It went way too long. I apologize for that. And I'll give you a few more problems to try. Keep your eyes on the AP stats, Trapper, Keeper, Thingamathing, go.